topic is the variational principle for Lagrangian one-forms.
Thank you very much. Today I'm going to talk about this title, variational principle for Lagrangian one-forms. As you see in my title, I will focus on the simple case I call one-form, and then later in this workshop, Frank will give the wider picture of the Lagrangian structure, and I believe that Sarah and Surit also will talk something about this also. At the beginning, I will mention briefly a little bit about cultural type, cultural Moser type system, which is from the basis kind of ingredient that we learn and then we cook up and then we get the general description of the Lagrangian. And then I will talk about the discrete, the structure of the discrete Lagrangian one form, and then its corresponding discrete variational principle, and then I will also talk about the continuous case. Okay. First, let me say something about cultural Moser type system. Well, it is kind of one-dimensional many-body system with long-range interaction with the repulsive force. This is the Hamiltonian, and this is the momentum, and this is the positions of the particles. And later, there is the model that discovered by Lagrangian and Schneider that was considered to be kind of relativistic version of this model. With this, we have this c, which is the speed of light, and if we take the limit on the c, then we get this Hamiltonian back. And we know that actually these two models kind of integrable in the sense of the order wheel. There is a set of invariants, which is they are in involution here. This is kind of well known, and there is also a Lux pair. We can find the matrix L and M, and then if we put into this Lux equation, then we will get equation of motion. Let me give you an example for the cultural Moser. Then this L and this M, and then if we put in here, then we get the equation of motion of the system. And then, well, once we know the matrix L, we can compute the invariance of the system by compute the power of the trace of the matrix L by this formulation. And then this is an example for cultural Moser system, which is actually the first one is just total momentum, and the second one is the Hamiltonian itself, and you get the higher order and in polynomial of the P with the complicated the potential terms here. And here the question, this is the question that we start with, that now we get this set of invariants that we can treat to be like a Hamiltonian set or Hamiltonian hierarchy of the system. And then the question is, what is the kind of Lagrangian hierarchy that corresponds to this set of Hamiltonian? And well, we can just compute the Lagrangian transformation straight away. But if you look at in the case of rationale, the relativistic case, it's probably really kind of difficult because the Hamiltonian not in the Newtonian type, because in the Hamiltonian is in kind of multiplicative form between the kinetic and the potential energy. And what we did, that we start from another way. We look at the discrete system that from these two papers, actually from Frank and his colleague, and for the cultural Moser and for the Lagrangian. And then from this, from this study, then later we can generalize idea to kind of to be the general description of the Lagrangian that correspond to kind of this system. And well, let me mention a little bit about the discrete for this system. Also, for cultural Moser, we have also the matrix L and M, and now here we get x is now is a function of n, and which is the discrete time variable, and then this notation x tilde that kind of that times that forward shift in the direction, and then we have also the discrete version of the Lux equation, and we get this is discrete equation of motion, and then from this we can guess the Lagrangian that corresponds to this, and we also have this term which is p is kind of lattice parameter, and then this equation that describes the dynamics of the system along the n direction, the discrete n direction. And here for the rational, we also have the matrix L and the matrix M, and we have here lambda to be kind of the parameter of system that we can take the limit and we get the Carol Moser back, and we also have to make the variable h, which we can solve it later from this Lux equation. Then we can solve for h with it, and we have the h and h tilde in this form, and then if we equating these two, then we get the equation of motion for the rational, discrete rational, and then this is the Lagrangian that we get. We also have the p here, but different. We need log here also. Again, then this equation describes the dynamic along the n direction. So now that if we introduce another direction in discrete time, that like we introduce that hat direction that corresponds with we have m here to be discrete variable for the hat, and then now x to be a function of n and m, right? And then now for the L, we just use the same L that we have before, and then we have different. Now for a temporal part, we have n with the hat direction, and then we do again with the discrete Lux equation, then we get h again, but different parameter q here, and then if we equating these two equations, we will get again the equation of motion that along the hat direction. But what we did is we equating this the first one with this h, then we get this equation, and we do the same with this one with this one, then we get this. These two form what we call the constraint equation, because it's now if you look at the equation, there's a mix between hat and tilde, but normally in equation of motion you get purely hat or purely tilde here. And then if we take the limit, the non-relativistic limit, you get for the case of Carol-Moser here. So what we observe from here, then if we look on the lattice, then the equation of motion will live on the horizontal or the vertical line here, and for the constraint that will live at the corner here, what we get here. And so now let me tell you about kind of the general description that for the discrete Lagrangian one form. Suppose now we have a set kind of the vector n that is a point in the kind of independent variable here, and then now the variable x is there's a function of this vector n. So we can, if you look at this picture, then suppose that we have the arbitrary discrete curve gamma here, then on the space of independent variables. So the action that corresponds to this discrete curve, that you just sum up this elementary bit here, every bit, then you get this action. That's what we get here. And so we introduce also the notation here. EI is a kind of the forward shift in the I direction. That's what we have here. And from actually, if you what we found is that actually this for arbitrary discrete curve can be constructed from this 4 basic type of discrete curve here, these four. And now we introduce this notation, the operator T that kind of forward shift in the I direction. And then from this four set of basis discrete, we get kind of a set of equation. That's here what we get is very interesting because we get here a set of equation that in principle that we could solve for the Lagrangian. Here, this set is contain both of equation of motion and also constraint. Then we can solve for the Lagrangian. Normally we could guess what form of the Lagrangian, but from this you could probably solve. And another property of the Lagrangian is called the causal relation for this one form, that actually for kind of local deformation, you find that actually the action for this, the action is invariant under this local deformation here. This is actually the direct consequence of variational principle on the space of independent variables. We do the variational principle here, then we get this that we call the causal relation. And let me give you this kind of example that for that of the system that possess one form structure. This is cultural motor, and then this Leishner, and recently also Raphael Bo also showed that the total type system also possess this structure also. And okay, let me move to the continuous case. Sorry, I have to in order to complete the picture, I need to talk a little bit about the continuous. Instead of discrete time variable, now we have the continuous time variable here, T1, T2, and so on. And then the Lagrangian also is a function of x, and also the derivative with respect to each time variable. But to make this simple, then we focus only for the first two four, right? For the T1 and T2, and then we need also to introduce the new variables s to be kind of to parameterize the time. So if we now consider this curve gamma here on the space of, again, independent variable T1 and T2, and then we can write down the action, which is the integral of the summation of the L1 and L2, right? And then if we use the variable s, we can write down in this form. And then from this action, we can actually do two steps of variational principle. If we concentrate on variation on the time variable, that we have to kind of deform the curve gamma. And the next one is if we do variation on the x variable, then which is we have to deform the curve that we call E gamma here. This with this curve that lives on up on this space. I mean, gamma is on this space. And from these two variational principles that we did, what we get is the first one we get kind of the closure relation here, and for the next one, for the variable x, what we get is that the Euler-Lagrange equation and also the constraint here. And well, recently Sulis also suggested that with another choice of basis, he got this form of Euler equation. But actually, we can show that this one and together with this one is actually equivalent to this one, but with the different choice that we perform on the variational principle. And here again, if you look at this, again we have a set of equations. We have the causal relation, we have Euler equation, and we have the constraint equation, would be in principle that we could solve for the Lagrangian. Okay, let me give you the idea how we can do that. Let me give you an example that for cultural motor that we get, and for the Leishner that have the structure that I talk about. what I highlight here, that what here is actually this, I mean, the kinetic term actually came up with the kind of that we perform the systematic continuum limit on the discrete case. Then we came up this kind of structure. I'm not sure that if we don't have the discrete case, we maybe have no idea how to guess the form of the kinetic term of and the higher Lagrangians. Okay. Now we go to kind of suppose now we take the answers form of the Lagrangian for the non-relativistic case. I mean for the Kurochiro-Moser case, that the L1 that we have V, and then for L2 we have W here, and then we would need to solve what is the form of the V and the W, right? Then, as I told you before, we have a set of equations, and we need to look what kind of form that we could get from this. And yes, we get equation of motion for the first one, and this is for the second one. I mean, and we also have the constraint here, and then from this constraint, if we do another derivative with respect to T1, I guess, yes, and then we eliminate the second order of derivative by using this equation of motion, then we will come up with the relation between W and V. And now if we look at the Cauchy relation, we will get this kind of relation. And then if we look at for n equal to 3, then we get this relation, which is actually the Weierstrass, I mean, elliptic function. Then we find that actually W informs the elliptic function here. This is for the Kurochiro-Moser case. Then we get the answer is the kind of the top case that actually is the elliptic case. And now for the rational, we do the same. We start with the answers form of the L1 and L2 with this is the potential, and this is we have the W here, also the U here, and then we do the same process. We start with equation of motion that's for the L1, and this is equation of motion for the L2, and then we have also the constraint equation, and then we cook up everything, and then we get this equation, which is we have the coefficient A, B, and C, which should be vanished, and then we set that the condition, but for A equal to 0 and B equal to 0, we get these two equations, and then yes, we eliminate U prime here, then we get this equation, and then from this we have two possibilities for the first one and the second one. But the first one is quite trivial. We don't interested in the first one, but for the second one, what we get at the end, that if we plug, if we use the second choice here, then we get this kind of equation, which is lead to this equation. And if we introduce this phi function here, then we get this expression that actually we can find the solution. We can show that actually phi is to be in this form. This is again that we have the elliptic case for the rational, and yeah, we can show that for the Cauchy relation. So what we get here is that we get the set of equations, and then we guess the form of the Lagrangian. We start with the answer form of the Lagrangian, and we plug everything into the set of equations, and then we solve, and then somehow we get kind of still have the integrable case. I mean the elliptic case. That is what we get, and yeah, I should stop here and yeah.
In the three-particle case with just a natural form of the Lagrangian with a potential, you got the Kurochiro-Moser from the functional equation. So can you show for n particles in general that you only get quadruple modes, or
what we did is now is only for 3.
only for 3?
Yeah.
Probably.
Probably
it's
I said that EV.
Yeah.
Or?
Maybe let me answer your question. As I shown in my paper, it is a general fact.
Yeah. Okay. It is true.
It's a completely general construction for any.
You didn't do the discrete case here.
We're working on that now.
I have a question. Because in physics we have this one form. We have the integral of some force. But the element, this is work done against the force. And if we can have same work done at another part, then that means the force is conservative.
Yeah.
Right? So that means that the force itself is the gradient of some scalar.
Mm-hmm.
So what is a scalar in here? And this is standard vector analysis, and then when you go to two forms, you also have Green's functions and all those things. So, but in one form, it's particular that you can define a potential. In two forms, you can derive a vector potential, so that you get the curl of a vector potential is your two form. So I'm asking, what are these sort of potential descriptions to your work?
I have
related to a tau function, I think.
Maybe not everything.
So the topology of the domain is going to be important here too. The topology of the domain is important here as well. Not just as simple as saying f is the gradient of potential, unless you know about the singularity structure.
Is there some singularities you have to worry about?
Yeah.
Let me comment on this. This closure relation is only holding on solutions of the equations of motion. And so it's not kind of like you can generally integrate this thing. You need to use the equations of the motion.
Yeah. Of course, you have much more structure than that. But if you have a path invariance, then you usually can define a potential.
This is a different setting.
Of course, it's different, but formally,
You cannot trivially integrate. You can
no. It's a different problem to integrate. Oh, further questions? Let's thank our speaker.